Great. Yeah. So welcome everybody. I'm Per Fuchs. Today we'll talk about Sortledton, a universal transactional graph data structure, work that has been done together with Domagoj Magan and Jana Gicheva. And we jump right into the problem we are solving. So the problem we are solving is graph use cases are diverse and dynamic. And by diverse, we mean that they have multiple graph workload categories within a single system. So for example, analytics, traversals, or graph pattern matching. Dynamic is simple. They require insertions and deletions. And we have two companies as examples for these kind of workloads. So Alibaba uses analytics and traversals in their anti-fraud pipelines. And Twitter uses traversals and graph pattern matching for recommendations. And both of them require up to 2 million edge up insertions per second. And this, in our eyes, leads to new challenges in graph data structures, namely striking a good trade-off for all these workloads in the neighborhood data structures. And we want three operations on these neighborhood data structures. We want transactional updates. We want them to be transactional so we can actually reuse techniques from static graph processing. Then we want efficient scans for analytics, and we want intersections for graph pattern matching. And as we see on the border of the triangle, it's always really simple to get any two of these operations fast, but all three of them is a bit of a trade-off. And that's also what we see in related work. So here we are looking at related work, Graph1, Stinger, LiveGraph, and Llama, and they're all on the left side of the triangle because that's easy to support. Then they have two different designs. They're either adjacency list-like or CSR-like. We only have one CSR-like here, one, because they're more complex to design. And then from 2021 on, we have a really great paper from Dean DeLeo and Peter Bonks, TCO, which also aims for the middle so they can support intersections. And they are also CSR-like. And then upcoming is Sortledton, our work, which aims there again for the middle, but is an adjacency list-like designer. We'll go into differences soon. And finally, a different way of looking at related work, only three of them are transactional. So then our contributions are the following. I will go through the first three in this talk: comparison of fundamental graph data structure design, analysis of access pattern in graph workloads, and then we propose, based on that, a simple dynamic data structure with it really close within the best static dateline for a universal data structure, the CSR, in both memory consumption as well as analytical performance. We have a fourth contribution, the design of a graph specialized serializable multi-version controlling system, but that's only in the paper. Okay, so with that, I start with a comparison of fundamental graph data structure design. First one on the left side is a CSR-like design, and here we have an index which maps vertex IDs into offsets into one gigantic data structure which keeps all edges in the graph. And this has one huge advantage. It has sequential vertex access. So if we access all neighborhoods in the order of the vertices, we get sequential access. But then on the other side, we have adjacency list-like designs. Again, they have an index mapping vertex IDs, but this time to point us to just anywhere in the memory, where then there is an independent data structure for each neighborhood. And that's a first advantage, because if the data structure is independent, for example, easy to parallelize on it, then we have cheap index maintenance, because the index always stays up to date, even if we insert edges, while the CSR-like one will move the index. And that's also what we see in both design, lazy index maintenance. And then we have the reuse of existing data structures, the third advantage of these data structures, because maps, we can use maps for the index, and we can use sets for the neighborhoods. And we can use any set, we can use any map data structure. Okay, so this is the comparison. Then we get to graph access pattern, and here we are looking at the example in inner PageRank loop, and we will see three different access patterns based on that. So first one, sequential vertex access. We access all neighborhoods in the order of the vertices. Second one, sequential neighborhood access. We access all edges in the order of the edge they are within the neighborhood. And then we come to random algorithmic specific access, where we access here, for example, the contribution array at the offset of the edge. And there's a fourth one, which we can't see in a PageRank loop, but in traversals, we see it often, random vertex access. And now the intuition behind our work is that optimizing for 2 and 3 has a higher impact because we have much more edges than vertices in the graph. And that's also what we will see in the evaluation later on, that this is actually a good intuition. So what I tell you next is a really simple design to optimize for 2 and 3. And this is it. So sorted and simple and sorted. We have a simple adjacency index. It's just a vector, and then it points to data structures for each neighborhood. And for hub vertices, we use the unrolled skip list. So an unrolled skip list keeps blocks of edges sorted in memory, and then links those blocks via skip lists. And then this supports all 3 operations because we have optimal scanning. And we measured that with 512 edges, we can't see any difference to a vector anymore because we amortize the random lookups in between. The second one is we have fast updates by splitting and merging these blocks. And the third one is we are sorted, so we can run intersections fast. There's one thing one needs now to do. And this is, again, an advantage of the adjacency list-like design. We can choose a different structure for small neighborhoods. So for small neighborhoods here, for example, of 2 edges, we can simply choose a vector. Again, we are supporting all 3 of these operations. And with that, I already come to the evaluation of the work. So we have update performance. How many updates can the data structure process? And the challenge here is to find out if the edge already exists. And then we have the graphalytic benchmark. And here we measure the slowdown of all graphalytics algorithms compared to what a CSR would give us. So a really good static data structure, right? Not in the presentation, mixing updates and deletions to expose aging effects and memory consumption over aging. Peter, do you have the time? Because I feel I'm
1 minute or so.
1 minute?
No, you continue.
Okay, so update. All right, so we have update performance on power law graphs, and what we see here is that both Sortledton and Teseo are much faster than the other systems because they have set data structures and can find out if an edge exists. We will jump over that slide, and then we come to graphalytics benchmark performance, and the graphalytic benchmark covers all different workloads categories: graph pattern matching, graph analytics, and graph traversals. 2 minutes? Okay. And what we see here, blue is Sortledton, that is us. We have really low overheads compared to the CSR, or no overheads compared to the CSR on all of these workload categories. We are only data structure who has that. Would like to focus on graph pattern matching for a second. So graph pattern matching is the most interesting. That is local coefficient correlation here, which is triangle counting. And as we see, Sortledton has no overhead. Teseo has a slight overhead for dense vertices, has a high overhead for sparse vertices because they need to do translation doing the computation. And all the other data structures can't finish within an hour, while CSR can finish within less than a minute. And that's the difference of having intersection support. With this, I come to my conclusions. There are 2, the adjacency list-like designs are simpler than CSR-like designs in design, while showing equal performance. And we need to store neighborhoods at sets to support graph pattern matching, updates, deletions, and consistency.
Thanks, Per. Are there questions on this talk? Can we see the gallery, maybe?
I can ask a question. Sorry. Hello?
Yeah.
I'm moving from rooms to rooms. Should I ask a question? Okay.
Yes,
so you looked into like Peter, and I forgot if you're a co-author, had a paper on packed memory arrays.
Right.
If you looked into data structures and their use for storing adjacencies, are there applicability? That's my question.
The question was actually for Per. So, but
for Per, not
for Per.
But you're the author, right, Peter?
Yeah,
you got a paper on DMA.
It's comparing against Teseo. So Teseo will be presented this VLDB by Dean Leo. And it contains packed memory array technology. It's not one packed memory array, but it's a blocked. It's like a fat tree where the nodes are packed memory arrays. So I think the answer to your question is yes.
So so there is a good case to use those for storing, say, neighborhoods. Is there like packed memory?
Is this a question for Per? Because Per disagrees. He
for
says
Per, yeah. So for Per, I was asking, like, Yeah, I was going to ask if he considered looking into packed memory arrays too as a data structure.
So we of course looked at SEO before we did this work, but I think packed memory arrays are just a data structure. You could do neighborhoods in it. Like for our data structure, you can also do a CSR-like design, and as Peter and Dean demonstrated, that was not the main question of my work. So the main question, or what I may answer to that, is the important thing for the data structure for neighborhoods is that you have blocks of edges continuous in memory so that you can amortize for the jumps. And one solution are packed memory arrays, another solution are block lists, block linked lists. And block linked lists are just way simpler than packed memory arrays.
Okay, now I would like to jump in with my own question, because, well, okay, this is interesting work. But one potential weakness is that if you have very many diverse blocks, over time you can run into memory fragmentation issues that will, well, lose your memory and also degrade your performance. Have you looked into that?
We looked into that in case that we ran all these analytics after adding each edge, edge by edge. And we had in random order. So what we got is building a graph with all the aging effects. We also ran the experiment, which has 10 times as many updates and deletions on the same distribution as Graph 500. And again, after running analytics, we didn't see any change of that data. Did you
use your own memory allocation library behind that, or just malloc?
Behind that is
from Linux.
Behind that is the memory allocation scheme from Intel, threading building blocks, the scalable one. Yeah.
Okay. Okay, that would be my question, but well, we can take this offline.
Yeah.
Of course, we are here in Copenhagen. I think, yeah, we should pause now. And then we have again exactly 5 minutes for the coffee break or the break, and we will resume like 5 minutes.